Hello, I'm Ganapathy Lakshmana Perumal. This is my final project for CSCI 104, Advanced Deep Learning at Harvard University Extension School. The topic is vector databases, the connective tissue between modern deep learning encoders and the applications that actually consume their output. Over the next 15 minutes, I'll cover the theory, implement 4 flagship indexes, benchmark them with real numbers, and wire the result into a Retrieval-Augmented Generation demo. Modern IVF-PQ do one operation more than any other. Given a query vector Q, return the k most similar items from a corpus of n. That single primitive powers, semantic search, recommendation systems, retrieval-augmented generation, deduplication, and multimodal applications like CLIP. Brute force works fine up to about 10,000 vectors, but at a million it becomes too slow for an interactive interface, and at 100 million it's hope. Approximate nearest neighbor algorithms and the vector databases that wrap them are how we make this tractable at scale. An embedding is a learned function that maps inputs into R to the D, where semantic similarity becomes geometric proximity. Sentence Barrett, Minilm, and Gega produce text embeddings between 384 and 4096 dimensions. CLIP embeds images and captions in a shared space. Whisper produces audio embeddings. Even the penultimate layer of a vanilla classifier is, in practice, a useful embedding. The common thread is that the loss function shapes the metric. The embedding is only as useful as the distance it induces. Why can't we just use a KD tree? The curse of dimensionality. On random unit vectors, the standard deviation of pairwise cosinistance shrinks from around 0.5 at d equals 4 to 0.03 at d equals 1024. The relative gap between the nearest and farthest random point collapses. Tree-based partitioning structures degrade to brute force above roughly 30 dimensions. The good news is that real embeddings are not uniformly random. They live on a low-dimensional manifold within R to the D, and modern N indexes exploit that manifold structure rather than fighting the worst case. 4 families dominate production. Flat is brute force, exact, O of n times d, the baseline. IVF, the inverted file, partitions the corpus into k-mean cells and only visits the nearest n probe at query time, typically 10 times faster. HNSW builds a hierarchical graph and greedy descends it. It currently holds the best recall latency Pareto on most workloads. Product quantization compresses each vector into bytes by quantizing subvectors independently, a 16 to 32 times memory reduction at the cost of recall. LSH was the theoretical ancestor, but is largely superseded today. Production systems often combine these into hybrids like IVF-PQ or UP-QQ-PQ. Let's zoom in on HNSW because it dominates our benchmark. HNSW is a multi-layer proximity graph FADK. Top layers are sparse, long jumps. Bottom layer contains every vector with short edges. A query starts at the top layer. Greedy walks toward the closest neighbor it can find, then descends a layer and refine. The 3 knobs are n, the edges per node, EF construction candidate list size during build, and F search, the same idea at query time. Build cost is O of n log. Num times m. Query cost is roughly O of log n times d. The downside is memory. About 4 times m times d bytes per vector, which is why HNSW gives way to IVF-PQ at billion scale. IVF-PQ is the heavyweight option. IVF gives you coarse partitioning into about square root of n k-mean cells. Then product quantization splits each vector into m subvectors and encodes each one with 2 to the b code, with m equals 8 and b equals 8. Every vector becomes 8 bytes, 16 times smaller than float 30. The distance computation becomes a table lookup, which vectorizes beautifully on modern CPU. The trade-off is recall, typically 0.55 to 0.85, but above 100 million vectors, where memory cost dominates everything else. On to the experiment. The corpus is 5,000 documents from 20 newsgroups via scikit-learn. The encoder is sentence transformers all 9L6 v2, 384 dimensions, 22 megabytes. That sweet spot between speed and quality. Embeddings are unit normalized to inner product equals cosine similarity. I built 4 indexes, flat for ground truth, IVF flat, with about 70 cells, HNSW with M equals 32, and IVF-PQ with M equals 8 and 8-bit codes. I sample 200 queries from the corpus and measure recall at 10 against the flat baseline. Everything runs on a CPU laptop and is fully reproducible. Here are the headline numbers. LE flat is 100% recall by definition at 67 microseconds per query and 7 megabytes of memory. IVF flat drops to 93.9% recall but speeds up to 47 microseconds. HNSW lands at 99.5%, recall at just 18 microseconds. 3.5 times faster than flat, with only 18% more memory. IVF-PQ recall is 40% here. That's an artifact of training PQ on only 5,000 vectors. The corpus is too small to fit the codebook well. The compelling number for IVF-PQ is the index size, 0.5 megabyte, a 13 times reduction. On a 100 million vector corpus, that ratio holds and recall climbs back into the 0.85 range. A single benchmark point misses the full picture. The real deliverable is the recall latency Pareto curve. I sweep and probe for IVF from 1 to 64 and EF search for HNSW from 8 to 256. IVF flat traces from 58% recall to perfect recall as latency climbs from 24 to 400 microseconds. HNSW traces from 98% per perfect while staying under 72 microseconds. HNSW dominates via EF lot at every recall level on this corpus. HNSW traces from 98% to perfect while staying under 72 microseconds. HNSW dominates via F flat at every recall level on this corpus. In production, you pick the cheapest point on the curve that still hits your recall service level objective, which for RAG is usually around 0.9. Because below that, the right document silently isn't in the candidate set and answer quality visibly degrades. ACE is a library. You give it a NumPy array, and it gives you top K. A vector database is a service. It adds persistence, replication, metadata filtering, hybrid keyword plus vector retrieval, CRUD APIS, and multi-tenant collect. I exercise ChromaB as a black box managed store on the same embeddings. Internally, Chroma uses HNSW via nslib with xquite for metadata. Grant, Weaviate, Pinecone, Milvus, OpenSearch, and pgvector all sit in the same category. The differentiation between them is in the surrounding distributed systems engineering, not in the underlying AND algorithm. Now we put it together as RAG, Retrieval-Augmented Generation. Step 1. Encode the user's query with the exact same embedding model used for the corpus. Step 2. The vector database returns the top case snippets. I use HNSW with EFS search 32. Step 3. A prompt template stuffs those snippets into the LM context with citation markers. Step 4. The LM generates an answer grounded in the retrieved evidence rather than its parametric memory. Optional fifth step. A cross-encoder re-ranks the top K for higher precision, and a grounding evaluator checks the answer site's real sources. Here's a sample query. How does encryption protect online banking? Here's a sample query. How does encryption protect online banking? The HNSW index returns 3 topical neighbors in under 0.2 of a millisecond. A thread on TLS and browser certificates from side. A discussion of public key versus symmetric encryption, and a thread on bank fraud from misc.security. All 3 are correct topical neighbors. That's the necessary precondition for the LM to ground its answer correctly. If the retrieval misses, no amount capability recovers it. So when do you reach for which? Under 10,000 vectors, used flat. Brute force is fast enough and exact. 10,000 to 1 million with memory available, use HNSW. That's the default in every modern vector database. 1 million to 100 million, switch to IVF-flat or IVF-NSW because pure HNSW memory becomes prohibitive. Above 100 million when memory is the binding constraint, IVF-PQ or OPQ-PQ for 16 to 32 times compression. With a GPU, IVF-PQ on the GPU runs 50 to 100 times CPI time. And whenever you need filtering, hybrid retrieval, or multi-tenancy, use a real vector database, not raw FAS. Some honest limitations. The embedding model dominates downstream quality more than the AND choice. Switching from minimum to a state-of-the-art encoder like BEGAM3 would change recall more than tuning HNSW or IVF. Production systems use hybrid retrieval, BM25, plus vector scoring fused via reciprocal rank, because pure vector search is bad at proper noun matching. Filter push-down matters. A naive post filter can destroy your latency budget. I did not benchmark distributed deployments, GPU indexes, OPQ, or LS. And 5,000 documents is a small corpus. The qualitative ordering of indexes generalizes, but the absolute microsecond numbers do not. To wrap up, a vector database is fundamentally a deep learning system component. Its inputs are the outputs of a learned encoder, and its job is to make those outputs queryable at human timescales. HNSW dominates modere corpora. IVF-PQ takes over under memory pressure. RAC composes that retrieval primitive into a complete generative AI system. As frontier models scale, their context windows grow, but never quite enough. Vector databases bridge that gap. The full code, the report, and these slides are in the project archive on YouTube and the course submission. Thanks for watching. Thank you for watching.